Okay, so today what I want to do is I want to wrap up um, randomized sketching for linear algebra. And I'm going to talk specifically just about k-means. And then we're going to start on compressed sensing. Okay, so k-means, we saw last time that k-means can be expressed as a constrained low-rank approximation problem. And then we saw this idea of PCP sketches, projection cost preserving sketches, that say if you use one of those, and really those are just themselves basically subspace embeddings and JL matrices to project your problem, it'll give you a kind of a sketch and solve approach to solving, to approximately solving constrained least squares problems. So did I just lose connection on my iPad? It seems. Hold on, sorry. Is my laptop still working? Can you all hear me?
Yeah, I can hear you.
Hear you and see you, but we can't see your iPad screen.
Yeah, sorry, I'm not sure how that happened. It seems that it just got disconnected from my Wi-Fi. Sorry, I have no idea how that occurred. I think I'm back now. Okay, good. So we saw that, this is a special case of constrained low rank approximation. Which implies you can sketch to dimension O of k over epsilon squared for sketch and solve. Just using a PCP sketch. Right, so I mean, the thing that's worth noting there is this bound doesn't depend at all on n, which is the number of vectors you're trying to cluster. It only depends on k, which is the number of clusters. So, if the number of clusters you want is small, it's a constant, then you've replaced the log n by k that you might be happy with that. I think I mentioned, it's definitely already mentioned in the course notes, that there's a newer theorem that shows that in fact you can almost get to log k. So you can sketch down to log k over epsilon over epsilon squared. So the k over epsilon is inside the log. And that also works for a sketch and solve approach. That analysis is very different from the analyses we've seen so far. It does use the JL, some kind of JL property, but it's a pretty elaborate analysis, which I'm not going to show you in class, but I put the reference in the course notes if you want to read the paper. But in any case, this bound, remember, is from the PCP sketch paper, which is this Cohen, Elder, Musco, and Persu 2015. That work already showed that, in fact, it already hinted that log k might be the right answer instead of k. What they showed is that if you map down to log k dimensions with the sketching matrix, and you'll see exactly what properties the sketching matrix needs to satisfy, but if you map down to log k dimensions, it already preserves the cost of any clustering up to roughly a factor of 9. So normally with sketch and solve, we think like we want a 1 plus epsilon approximation. They didn't know how to prove 1 plus epsilon, but they did prove 9 plus epsilon, which is something. So at least you get a constant factor using only log k dimensions. So what I thought is I would just show you that proof, and then we'll end this kind of chapter and move on to compressed sensing. Okay. So the theorem is that say A is given as well as k and epsilon are given. And what we want to do is we want to k cluster, we're doing k-means clustering, k cluster the rows of A. Okay. Now say pi is a sketching matrix. So it sketches the rows of A. So it's going to be right multiplication. It's going to map the vectors from D dimensions down to M dimensions. So say pi is an arbitrary and satisfies certain conditions, which, we'll fill these in later. We'll see what we need. And also define P star is the optimal clustering. So P star is the minimizer of identity minus P A for Venus norm squared over all K clusterings. Over all K clusterings P. These are projection matrices. Remember, any K clustering we saw last time has a corresponding orthogonal projection onto a subspace of dimension at most K. So P star is the optimal. P tilde star is the argument for the sketch problem. And let's say P tilde is some other K clustering, which is a gamma approximately optimal solution for the sketched version, such that if you look at the identity minus P tilde applied to A pi transpose, so applied to the sketched problem, then this is at most gamma times identity minus P tilde star A pi transpose for Venus norm squared. Right, so this is related to a question that someone asked last time. I think maybe it was Edward. The question was, okay, but K means is an NP hard problem. Even if you sketch to lower dimension, it's still NP hard in the lower dimension. So how are you going to solve it there? So what we're saying is, look, okay, once you sketch down, run some approximation algorithm that doesn't solve it exactly, but it gives you a gamma approximation. That's P tilde. And the claim is that P tilde will be roughly a 9 gamma approximation for the original problem. Then we'll have that I minus P tilde A. This is there's no pi now, so this is the non-sketched version, is going to be at most 9 plus O of epsilon times the true optimum. There's a gamma times the true optimum. As long as you know these conditions are satisfied, these red conditions, which I didn't write down yet, but we'll see as we do the proof. We'll see what conditions we need, and we'll see like what kind of sketch size can you get away with to make it happen. It's going to turn out that you can get away with m being something like log k over epsilon squared. Okay, so if you think of epsilon as a constant, you just want a constant factor preservation. There's already a 9 there anyway, so you're not going to get 1 plus epsilon. Then you basically need log k, O of log k dimensions to preserve things up to a constant factor. So before I show you the proof, are there any questions about this? About the statement of anything here? Okay. So if not, let's start the proof. So let's prove that. I'm gonna decompose, and we did this kind of decomposition when we analyzed, what do you need to be a PCP sketch? If you remember, we decomposed A as AK plus A minus K, which if you think about it is really PK plus 1 minus PK, where P is like UK transpose. It's like the optimum rank K orthogonal projection, not just clustering projections, but like any rank K projection. So now we're going to also do a decomposition, but instead of using UK transpose as our projector for the decomposition, instead of using the optimal rank K projection, we're going to use the optimal clustering projection in our decomposition. So we're going to decompose A as P star A plus identity minus P star A. So that's the projection onto the orthogonal subspace. And I'm just going to, for ease of writing, so that I don't keep writing long things, I'm just going to call this bar B, not like Ken and Barbie, but there's a bar on the B. Okay. And this is B. So I'm looking at now, what do I want to understand? I want to understand the identity minus P tilde applied to A for Venus norm. Okay. I'm going to write A, as I said, A is B plus B bar. Oh, yeah. I don't have to say bar B. I can say B bar. Okay, good. B plus B bar. And then now I'm just going to do triangle inequality. So this is at most identity minus P tilde applied to B plus identity minus P tilde applied to B bar. And we already see that the second term is easy to handle, right? Because a projection I minus p tilde is itself a projection operator. It's a projection onto the orthogonal space. Projection operators do not increase Frobenius norms. They don't increase L2 norms, and a Frobenius norm is just the sum of, Frobenius norm squared is just the sum of L2 squareds of the columns. So all the columns have their norms not increased. If anything, maybe potentially shrunk. So this thing here is already at most the norm of B bar, which, by the way, is also known as, if you remember what B bar is, this is just like the square root of opt. Right? Just look at what B bar means. B bar is this thing. Right? It's the residual after you do the optimal k-means clustering. So what is the opt cost? The opt cost is the squared Frobenius norm of that thing. Here we just have Frobenius norm, not squared Frobenius norm. So it's the square root of opt. Okay. The only reason I didn't square things from the beginning is because we're going to do some triangle inequalities, and squared Frobenius norm doesn't satisfy triangle inequality. But we're going to, at the end, we're going to get something, and then we're going to square both sides at the end. So this is eventually going to become opt. Okay, so just be a little patient there. Okay, so now so now what's the next thing I want to say? Okay, the next thing I want to say is, look, so so let's say A is n by D, right? What's the dimensions of P star A? Anyone? I know there aren't that many people here live, but don't be shy. So A is n. Yeah, P star A is n by D. But notice there's something special about P star A. How many distinct rows? So yes, it has n rows, but how many distinct rows does P star A have? I claim that P star A has a lot of duplicate rows. Why is that? Do people remember from last lecture? Right.
I was just for how the k-means.
Right. So remember, we defined like, remember, why was k-means a special case of constrained low rank approximation? It was because, given any k partition of the points, we could define this matrix xp, where let's say p is the partition, and xp was this n by k matrix where if point I is in partition J, you put a non-zero there. Otherwise, if it's not in partition J, you put a 0. And then we normalize the columns to each have a unit norm. And the observation was that XX transpose was a projection matrix because X has orthonormal columns, right? And then I said this, if you apply XX transpose, the projection matrix to A, it maps each row of A to the centroid of the partition it belongs to, right? Which means P star A, each row of P star A is the centroid of some partition for that k-mean solution. There are only k partitions, so there are only k centroids here. So there are only k distinct rows of B. B only has k distinct rows. Okay. Good. Now, why is that relevant? That's relevant because I would like to say, remember now, when we first ever talked about k-means in this course, it was when we were talking about JL. And what did we say at that time? We said that if JL preserves the distances of all the points, then it preserves the cost of any partition, of any k-means clustering. Because we were able, if you don't remember this, you can review it in the course notes back in the JL section. It's there. You could rewrite the objective of k-means as the sum of square distances within clusters. So like sum over each cluster, you normalize by the size of the cluster, and then you sum over all pairs of points in the cluster and look at their distance squared. You can rewrite k-means, the k-means cost in that way. So as long as you preserve all the distances of all the points, then you preserve the cost of any clustering. Okay? And since there are n points, you just do JL. I can preserve all distances between n points using log n dimensions. But here's the beauty of this now. B doesn't have, B has n points, but it only has k distinct points, right? If you think of B as like this artificial multi-set of points that I'm trying to cluster now. And I'm clustering it using P tilde, right? I minus P tilde B is exactly like I'm k-means clustering the rows of B. But since B only has k distinct rows, I only need log k dimension. I only need log k over epsilon squared dimensions to preserve the cost of any k mean solution to B. In particular, the cost of p tilde. Does that make sense? So what I would like to write is that this is at most, let's say, root 1 plus epsilon. I just put root 1 plus epsilon. Usually I talk about preserving Frobenius norm squared. Since here I have Frobenius norm and not Frobenius norm squared, I'll just square root the 1 plus epsilon as well, which is convenient because I'm going to have another one later, and then I get rid of the square root. Doesn't matter. So this is going to be like I minus p tilde b pi transpose Frobenius norm. And then plus I had that b bar there. Right? So the point here is I'm saying that as long as pi has that, so here's one of the conditions. Remember I said I have these conditions over here, these conditions. So one condition I want is that pi preserves distances between all pairwise distances between the rows of B. Okay, and since B only has k distinct rows, that this condition holds as long as m is at least something like log k over epsilon squared. This is just JL. Okay, so that's one condition. Does that make sense? So that's kind of one observation, one maybe sneaky observation that we're going to use. And then I'm going to write that, B is equal to A minus B bar. So this is equal to root 1 plus epsilon I minus P tilde A minus B bar pi transpose Frobenius norm plus B bar. And then now what I want to do is I want to collect like terms. So this looks something like, this looks something like A minus P tilde A. Okay. Then I have a minus B bar minus P tilde B bar. Right? Okay. So now I'm going to do I'm going to decompose things like that. This is just using the fact that B is equal to A minus B bar. Okay. That's the definition of B bar. So now I can do triangle inequality again. And this is at most root 1 plus epsilon A minus P tilde A. Or let me just write it like this. Identity minus P tilde A pi transpose, of course. Frobenius norm plus root 1 plus epsilon identity minus P tilde B bar pi transpose Frobenius norm plus B bar Frobenius norm. Okay, good. So that's just a triangle inequality. And then now, again, I can use the fact that projection matrices do not increase Frobenius norms, which means I can just ignore this projection matrix right here. And then we talked about this last time on Monday. We said, look, if you have a fixed vector and you take a random matrix pi, it's going to preserve its norm with high probability. That's distributional JL. And we said not only will it preserve the norm of a fixed vector with high probability, it'll also preserve the norm of a fixed matrix, the Frobenius norm of a fixed matrix with high probability, as long as it satisfies the JL moment property. Does that sound familiar? So I want to use that right here, and I'll say that as long as pi satisfies the JL moment property, it's going to preserve the Frobenius norm of B bar with high probability. So that's going to give me another square root 1 plus epsilon. So this thing is going to be at most 1 plus epsilon times the norm of B bar, which I can combine with the other norm of B bar. So here what I'm using is just, here this requires M to be at least basically 1 over epsilon squared. That's it. This is just the JL moment property. And the lemma we proved last time saying JL moment property also implies preservation of Frobenius norms of matrices. And then here what I'm going to say is that now, this A should not be inside the paren. So here what I want to say is P tilde is, it's a gamma approximation to the opt, right? So I can say that this is at most now root 1 plus epsilon. And remember that the cost should be Frobenius norm squared. This is not Frobenius norm squared, this is Frobenius norm. So it's root gamma. So root 1 plus epsilon times root gamma times, I can replace it now with the actual opt for the projected problem. And now here I have a 2 plus epsilon times b bar. And now again, we've already seen this before talking about sketch and solve. P tilde star is only better than P star for the projected problem because P tilde star is the optimal solution to the projected problem. So this is at most 1 plus epsilon root gamma times, I can replace that with an actual P star. Okay. And then now what do? I'll say again the same thing that I just did for the last red box. I minus P star A is a fixed matrix. So with good probability, pi preserves it as long as it satisfies the JL moment property. So again, by the JL moment property, I just need M to be at least 1 over epsilon squared. This is the JL moment property. I get that I can remove the pi. So this is at most root. Now I have 1 plus epsilon. 1 plus epsilon root gamma times identity minus P star A without pi plus 2 plus epsilon B bar F. Okay. Now, what is B bar? B bar is identity minus P star A, right? This is B. So I mean, these two things are the same thing. These are the same thing. That's the same thing as B bar. So now this is basically, and also I know that gamma is at least 1 because gamma is your approximation factor. You can't be better than a 1 approximation. Okay. So this is a little sloppy. You could say something a little bit better, but I'll just like artificially inject a root gamma here. That's definitely an upper bound because gamma is at least 1. So that means that this whole thing is equal to something like now what, 3 plus 2 epsilon times root gamma times exactly what I wanted, identity minus P star A for Frobenius norm. And then now I just compare what I have. I have this. And then what did I start with? I started with this at the top left there. And then now I just square both sides. And then that removes the root on the gamma too. And I'm done, right? That's exactly what I claimed. So that's roughly 9 plus O of epsilon, right? 9 plus O of epsilon times gamma times opt. Any questions about this? That's basically it.
In the middle, why are you able to drop the I minus P tilde and the pi transpose to get a root 1 plus epsilon?
Oh, why did I drop the identity minus P tilde?
The part that's like scribbled out in orange.
Yeah. Oh, right. Because it's the same. It's actually the same thing that we did up here. Remember here, I also dropped it to get here, right? And the reason is just it's a projection matrix, and a projection matrix can't increase the norm of any. It can't increase the Frobenius norm of a matrix if you apply it. Like it's the same reason. Like if you apply a projection matrix to a vector, you're only going to potentially decrease the norm, not increase the norm. So does that answer it?
Yeah.
Okay.
Then the root 1 plus epsilon comes from JL.
Yeah, that because there I dropped the pi. Right?
Yeah.
So that's basically that's the JL moment property. Yeah. Okay. Great. Any other questions? That's it. So okay. So that. Oh yeah. No, you had something else.
Oh, and so we wanted. Oh, I guess you squared that and you get the epsilon squared. Doesn't. Okay. Never mind.
Yeah.
I was confused that the.
Oh, the very end,
epsilon was squared, but that's fine.
Okay. Oh, but now it's all good.
I thought I was confused, but.
Oh, but you're not. Okay, good. Okay, great. So that's it. That's all I wanted to say about this. And now let's move on to other stuff. I thought that the part about like, I don't know, I personally admired the kind of, especially this one step, which is right, kind of this step, the observation that like I minus p tilde b can be viewed as a k-means clustering cost of a multi-set of points that only has k distinct points. Therefore, I can apply JL with a smaller effective n, where n is only k. I don't know. I thought that was pretty cool myself when I first read it, but in any case. So let's move on to compressed sensing now. That's all I wanted to say about that. I think I minus p star a is exactly bar b. So you only reserve bar b, which you already, yeah, that is true. Yeah, so that's right. So I think what Edward is saying is just that this condition and this condition are actually the same condition. So you don't actually need to condition on two separate events. They're the same event. Is that what you're saying?
Yeah.
Yeah, right. They're the same. That's right. So there are only really two events here. One is that your JL on the rows of B, and the other is that pi preserves B bar, which is the same thing as identity minus P star A. Okay, great. In fact, maybe I goofed that myself in the, wait, actually, is that really? Let me actually, you know what? I think, yeah, that's right. There's something goofy in the notes, which I'll fix. The notes did not, they did, there's some typo there. Okay, great. So let's continue. Okay, so compressed sensing. So the idea here is, let's say X is approximately sparse in some known basis. And we want, let's say approximately sparse, want to approximately, and let's say it's undimensional. We want to approximately recover X using few linear measurements. So what I mean is we want to recover some X tilde given pi X such that like X minus X tilde is small. So the rows of pi are the measurements. And so pi is going to be like a sketching matrix. It's going to look something like that. Okay. Right, so a linear measurement is just like the dot product of one of these rows with X. Now, what if X is not just approximately sparse, but X is actually sparse? Like, let's say that I promised you that X has at most K non-zero entries. Then what would you do? This is something that you've seen already, I think. Yes, you have seen it. Does that sound familiar? If I promise you that X is sparse?
Is this the
K-sparse recovery.
fast?
Yeah. Go ahead, sorry. Yeah,
I was
K-sparse
going
recovery,
fast.
I think. Someone said it, right? Recoveries. Yeah, this is K-sparse recovery. So, right, remember we saw this before. If X is actually K-sparse, you would just set pi to be something like, 1 x1 squared, x1 to the m minus 1, 1 x2 squared, x2 to the m minus 1, etc. It'd be this like van der Waals matrix. So that if you look at any m by m submatrix of this, it has full rank. So as long as you choose the xi's to be distinct, if you look at any m by m submatrix of this, it's invertible. So as long as pi has m to be at least 2k, we saw last time. So this is what we did for k-sparse recovery. I mean, here, we called it a data structure back then, but in fact, it was just a bunch of linear measurements, right? Right. So that would just be it. And then if you want to recover x given pi x, I mean, there is the exponential time solution of loop over all m by m submatrices of pi, solve a linear system, return the first one you get that gives you back something that's actually k-sparse, because it might give you back something that's only 2 k-sparse, and then you chose the wrong set of columns. But if it gave you back something that's actually k-sparse, then you know that it is in fact the right solution, right? Because the property of this matrix is that, I mean, it's designed so that all distinct k-sparse vectors have distinct images. So if you actually get a k-sparse vector back from inverting, that must have been the one you started with, since they have distinct images. Okay, and so I mean that's an exponential time decoding algorithm to get back x, but there is in fact a polynomial time one. I mentioned this last time. I didn't actually describe the algorithm. If you're working over a finite field, the recovery algorithm is called syndrome decoding. This is very closely related to, in fact, it's not as close. It is exactly the same algorithm as decoding Reed-Solomon codes efficiently, it turns out. Now, if you're not working over a finite field, but you're working over like the reals, it turns out that was actually studied even earlier. There's a fast recovery algorithm that's called Prony's method. And if you read on what Prony's method is, and you read what syndrome decoding is, you realize that they're actually the same thing, just over different fields. So syndrome decoding was actually discovered by Prony much earlier. This is an algorithm from the late 18th century, okay, 1790 something. I'm actually not sure why. There's a reason, I'm sure, but I'm not sure exactly what Prony's motivation was for developing this. But he did come up with this algorithm back in the late 18th century. Okay, so that's it for exactly k-sparse vectors. But you might have a vector which is not exactly k-sparse. You often have a vector which is not exactly k-sparse, but it's approximately k-sparse. And what does approximately k-sparse mean? So approximate sparsity what I mean is that there exists a z such that x minus z is small in norm. Okay. And for a lot of norms that that we've been talking about, like LP norms, for example, what should z be? Z should just be like project x onto its top k entries in magnitude. So like for many norms that we've been talking about, z is just like what I'll call x head k. So I can write like x projected onto the top k coordinates in magnitude, and then there's like the tail. This is k-sparse. So the error is like the norm, basically, of x tail. Okay. And this should also look familiar because it's actually quite, I mean, I think I've already defined this notation back when we were talking about the heavy hitters problem. I mentioned that, when you like algorithms like the Countman sketch and the Count sketch, not only do they provide error that's proportional to the L1 norm of the vector, so let's say divided by k, but actually the norm of x tail k divided by k, or x tail k divided by root k in the L2 case. Okay. So we've actually already seen compressed sensing from the Countman and Count sketches. So if you think about Countman, if you set the failure probability of Countman to be much less than 1 over n, and then you point query every single coordinate of x, and you ask, kind of give me an estimate of xi, it'll return to you some xi tilde that is close to xi by the Countman guarantee, by the error guarantee. So, the fact that you're close for all I, x tilde I is close to xi for all I, that basically means you have an L infinity norm guarantee. And essentially what countmin tells you is that x minus x tilde L infinity norm is going to be at most something like 1 over k times the norm of x tail k. And here, how many rows do you need in the count-min sketch? You basically need k times log n rows, right? Because count-min sketch, you need to have O of k. You know, if you think about the count-min sketch as this grid of counters, you have O of k columns, and the number of rows you need is log of the inverse failure probability in the count-min sketch. What's your failure probability? It's something like 1 over n, because you have to union down over all the coordinates. So you're going to have log n rows in this grid of counters. So it's like roughly O of k by O of log n. So it's O of k log n. And we didn't talk about it, but it's also possible to prove that you can get like an L1 guarantee for count-min sketch as well. In particular, you get something like x minus x tilde L1 norm is at most something like 1 plus epsilon times x tail k L1. And to do that, I think it's going to be something like m has to be at least, it might be k over epsilon or k plus 1 over epsilon, but to be safe, I'll say, it's something like k over epsilon. Okay. So what you just do is like, you do, just project x tilde onto its top O of k coordinates. So do exactly what I said. Do count-min sketch, point query every coordinate. Now you have n coordinates, you have estimates of n coordinates. Just zero out all of them at the top, k or 2k or something, and you can prove that that will give you this L1 guarantee. Okay. And similarly, we saw this also with the count sketch. We basically replace L1 with L2. So we said that x minus x tilde L infinity norm is at most 1 over root k times x tail k L2 norm. Again, with m being O of k log n. And you can also prove an L2 kind of guarantee as well. Same thing, you just project onto the top of k coordinates. Okay. The thing to observe about both of these algorithms is that they are they satisfy the for each or non-uniform guarantees. So that's just some jargon from the compressed sensing literature. You might see these terms. They mean the same thing. For each or non-uniform means the same thing. What does it mean? What does it mean when someone says that count sketch or count min are non-uniform approaches to compressed sensing? Okay. By the way, does this all make sense? So notice that, by the way, if x actually is k-sparse, the norm of x tail k is 0, right? So count min and count sketch will actually recover the exact vector with good probability if it actually is a k-sparse vector. Okay. But if it's not exactly k-sparse, but it's approximately k-sparse, they'll give you error that depends on just how not sparse it is. It depends on the norm of the tail part. Okay? So that's kind of good. That's the kind of thing we like to see in compressed sensing. Okay. So what does this mean, this for each guarantee or non-uniform guarantee? So let me write down again some jargon. So this is jargon now. So when someone says non-uniform, what they mean is that for all x in Rn, the probability over, let's say, you have some sketching matrix pi. There's some measurements you're making, and you also maybe have some recovery algorithm, which maybe it's randomized. The probability that x tilde equals alg. So alg is the recovery algorithm, which takes as input pi x, and it also takes as input pi. It knows what pi is a good approximation to x is, at least 1 minus delta. Okay. So for any fixed vector x, which is this thing you're measuring, you have a fixed vector x that you want to recover. You look at, what's the probability that my measurement scheme, my pi and my recovery algorithm allow me to recover a good approximation to x? That's high. A uniform scheme, on the other hand, or also called a for all scheme. This is also called a for each scheme. What does that mean? It could be randomized or it could be deterministic. It doesn't have to be randomized. But let's say that it is randomized. Then what it means is the probability over pi in the algorithm that for all x tilde equals alg pi x pi. I mean, I guess I don't really need to say that alg takes pi as input, because you can imagine that pi is part of alg, right? Pi is hard coded into the source code of alg, because since alg is random, it might as well just have pi in its source code. The probability that is a good approximation to x is at least 1 minus delta. Does that make sense? So it says, like, think that now pi. Imagine that there's no randomness. Imagine that pi is actually deterministic. What this is saying is that there's one measurement scheme. You're going to do these m measurements, and no matter what your x is, my measurement scheme together with the recovery algorithm will work. It will recover a good approximation to x. Okay? So it's a stronger statement than the non-uniform scheme. So, maybe you have a bunch of different x's. You have x1, x2, x3 up to x100 that you're trying to do some sketching and recovery on. The non-uniform scheme, I mean, you could get your scheme to work for all of them if you just make delta be smaller, make delta to be delta over 100 so you can union bound. But the beauty of the uniform scheme is that kind of once you have the scheme, once you have pi and the recovery algorithm, it just works forever. No matter how, for all x's you give it in the future, it's going to work. So I've already told you that we basically already have non-uniform schemes that work. Countman sketch, count sketch, basically any heavy hitters algorithm works, or point query algorithm works. So what I want to show you today is that, in fact, there's a very good uniform scheme. And we're going to talk more about this next week as well. By the way, just recall, and I'll send a reminder, we only have class next week Monday because Wednesday is a university holiday. It's, I think, Veterans Day. So we'll have class Monday, and we'll talk more about compressed sensing then too. But in any case, I want to show you that there's a good uniform scheme. So questions about these definitions, about the jargon? Okay. So in order to develop a good uniform scheme, I'm going to use a concept that we talked about before, which is the restricted isometry property, or RIP. And if you remember, we talked about this when we were talking about the Kramer-Ward theorem. If you take an RIP matrix, you multiply it by a diagonal matrix with random signs, that will give you a JL distribution. Okay. So we covered that back when we were talking about fast JL. But, actually historically, Kramer-Ward, the reason, so as you're going to see, you can get RIP matrices from JL. Kramer-Ward, the surprising thing when that paper came out in 2011 was they showed the converse, that if you have an RIP matrix, you get JL. So that was in 2011, after people had already been doing compressed sensing for a number of years. Compressed sensing really became hot, I think, in you'd say 2005, 2006. So people had been, working on compressed sensing. They had been coming up with different RIP matrices, proving that various distributions have RIP. And, one of the first proofs was using JL as a black box. In fact, it's very similar to I think problem 1 on PSET 2, which is due next week Monday. That you can show that JL implies RIP. So anyway, what is RIP? Let's recap. Pi satisfies the epsilon k restricted isometry property if for all k sparse vector z, if you look at pi z L2 norm squared, it's at most 1 plus epsilon times ZL2 norm squared. And it's at least 1 minus epsilon times ZL2 norm squared. So note, an RIP matrix is, if pi is RIP, that implies that it's an epsilon subspace embedding for n choose k different subspaces at the same time. Right? Basically, just look at the subspace spanned by any subset of k standard basis vectors, and just look at all n choose k such subspaces. If you preserve, RIP is equivalent to saying that you're a subspace embedding for all these n choose k different subspaces. And as you maybe have proved already or will prove soon as you work on pset 2, one way to show that a matrix, one way to get a subspace embedding for a k-dimensional subspace. Oh, these are k-dimensional subspaces. K-dimensional. If you want a subspace embedding for a k-dimensional subspace with high probability, with probability 1 minus delta, for a subspace embedding, you need M to be at least something like k plus log 1 over delta over epsilon squared. Oh, actually, I'm being a little. Let me be a little careful. Am I doing part of your pset for you? If I am, then maybe I should stop. Yeah. So let me. I think I'm getting very close to doing one of the problems, which was an easier problem, but we're going to show in part 1 of the problem. And if you look at pset 2 problem 1, you're going to end up needing M to be at least this to be a subspace embedding with probability 1 minus delta. And that kind of already is very closely related to problem 1b on your pset, which was an easy problem anyway, given this. But I guess anyone who's watching lecture is now rewarded for basically seeing an almost solution to problem 1b given 1a, which was not supposed to be a complicated problem part anyway. Okay, so basically JL, all I'm saying is that JL implies subspace embedding. Subspace embedding implies RIP with a low enough failure probability. Therefore, JL implies RIP. So you get an RIP with M is at least k times log of some constant En over k over epsilon squared gives RIP with high probability. Okay. And if you think about what RIP means, it is somewhat of a natural generalization of the Vandermonde approach. Like, what is the Vandermonde approach really saying? It's saying that if you look at any submatrix, of pi obtained by obtained by taking k columns, it has full column rank. Okay. In other words, what that means is if you look at any submatrix of pi obtained by taking these k columns, if you look at the pi transpose pi, it doesn't have any eigenvalues which are 0. Okay. Pi transpose pi is a real symmetric matrix. It has real eigenvalues. None of those eigenvalues are 0. All the eigenvalues there are positive. Okay. So, that's the same thing as looking at the singular values of pi transpose pi, right? The eigenvalues and the singular values of pi transpose pi are the same thing. So all the singular values of pi transpose pi are at least are strictly well, okay. So singular values, the way I define them, I always define them to be just take the positive ones and ignore the 0 ones. But eigenvalues, none of them are 0. They're all positive. And kind of RIP is like enforcing something even more. It's saying that not only are all the eigenvalues of pi transpose pi, when you zoom in, when I say pi transpose pi, I really mean like zooming in on some subset of columns of pi. So let's say pi s. Pi s is the projection of pi where you only keep the columns that are in S. So look at pi s transpose pi s, where S has size k. It's saying that not only are the eigenvalues positive, but they're all very close to 1, right? They all have, all the eigenvalues are between 1 minus epsilon and 1 plus epsilon. So it's a kind of a stronger version of the van der Waals matrix in that way. Okay. So a natural way to recover a k-sparse x given pi x is as follows. Solve the following program, the following optimization problem. Minimize the L0 norm of z, which is just, when I say L0 norm, I just mean the support size. Subject to pi z equals pi x. Okay. That will find the sparsest solution that has the same image. So in particular, like if pi were the van der Waals matrix, for example, and x were k-sparse or sparser, this would be guaranteed. This would be guaranteed to find x, right? This would be guaranteed to return x. The problem is that this is intractable. In general, it's NP hard. Finding a solution of a linear system with minimum support size is an NP-hard problem. And it's actually one of the first discovered NP-hard problems. There's this compendium of NP-hard problems from Gary and Johnson back in I think 1979. And it's in that compendium. So it's kind of one of the first, not the first, but one of the first problems that was known to be NP-hard. So what you do is you relax to, instead of minimizing the L0 norm, you minimize the L1 norm. Subject to pi z equals pi x. And this is a linear program. And it's known as, and this linear program is known as basis pursuit in the literature. Just to be clear, like the reason it's a linear program is you could just say that for all I, yi is at least zi and yi is at least minus zi. And then now you also have pi z equals pi x, and you want to minimize the sum of the yi's, right? These two constraints force yi to be the absolute. The fact that you're minimizing yi and those two constraints means that yi is going to be forced to be the absolute value of zi. So this is in fact a linear program. So you can solve it in polynomial time because LPs can be solved in polynomial time using interior pointer ellipsoid or whatever. So the claim that we're going to see the proof of is that if pi is RIP, then if x tilde is the solution to basis pursuit, we're going to have the error guarantee x minus x tilde L2 norm, okay, is at most O of 1 over root k times x tail k L1 norm. Okay. I mean, I'm being now a little informal here because RIP with what parameters exactly, but we'll see that when I give the actual theorem statement and proof. But that's basically where we're going with this. Okay. The fact that, so now this is a uniform scheme, right? Because RIP is, it has nothing to do with any particular x. It's a property of pi. It's not even a random property. There could be a fixed matrix which satisfies RIP for a given k and n. So take a fixed matrix pi which satisfies RIP, solve this linear program, which there's no randomness in it at all, and you will get a good approximate. You will get an approximately good recovery of x. So this is uniform. This is a uniform guarantee. So I will write down the claim precisely in terms of kind of what parameters you need for the RIP, and then we'll prove it. And before I do that, I also want to give you other examples of how to get RIP matrices deterministically, like not just using JL, but is there a fixed deterministic RIP matrix? How do you get one? I'll say a little bit about that, and then I'll prove this claim. But this is where we're going. So any questions about any of this? Okay. So before we prove this claim, how do I get an RIP matrix? So one, we said you can get it from JL. Two, you can get it from incoherent matrices. And we'll see that. This is P set 1, problem 1. And 3, and we also saw incoherent matrices in class when we talked about, oh, did we see it in class? Maybe it was just on the P set. And 3, just other, ad hoc explicit constructions. But these unfortunately right now are rare and hard. Okay. So this is going to give you some m to be O of k log n over k, or en over k, let's say. This is going to give you, you'll see, O of like k squared times polylog n. And this is going to be like O of like k to the 1.999 polylog n, only for k very close to root n. And I'll say a little bit about this, but that paper, let me give the reference. It was a bunch of number theorists, or it was a bunch of people who do a lot of pure math, some of whom were number theorists. But that's Bourgain, Dilworth, Ford Konyegan, as well as Kutsarova. That was in 2011, I believe. So, I mean, Bourgain and Konyegan are like really hardcore analytic number theorists. I think the others might be more combinatorialists. But this was not an easy result. This was some very complicated number theory. And I mean, the reason they were doing it is there's this sub area of computer science, of theoretical computer science, called pseudo-randomness. And essentially what one of the things that it does a lot is tries to get explicit constructions of objects that are useful in computer science. So you might be able to prove that something exists using the probabilistic method. Pick a random such thing. Oh, this thing is what I want with high probability. That's exactly what item 1 here is, JL, right? Pick a random Gaussian matrix, okay? And then by applying the distributional JL lemma, I can show that this random Gaussian matrix satisfies JL with high probability. Now, therefore, I've shown that RIP matrices exist, that in fact, there's a randomized way to get one with high probability. Although we don't know how to check it. We don't know an efficient algorithm, like given a pi, does this have RIP or not? We don't have an efficient polytime algorithm to check that. So people, pseudo-randomness people were very curious. They were like, well, we know they exist because we have probabilistic arguments showing that they exist. Is there an explicit construction of one, right? Like that uses no randomness whatsoever. It's just like, here's an algorithm, you give it K and N, and then you give it maybe I and J, and you ask it, tell me the ijth entry of this RIP matrix you have in your head. It should give it back to you. It should give that answer back to you very quickly. Or even easier, given K and N, just print out an RIP matrix in time polynomial in N. Like we do not, to this day, we do not have that. We do not know such a thing. Okay. The only thing we have is like item 2. Or I should say, we do have such things, but they lose out on the parameters. I know that an RP matrix exists with roughly k log n rows, right? K log n over k rows. That's what JL tells me. I would like an explicit construction that achieves that. The best we know is incoherent matrices. So as you saw in PSET 1, problem 1, Reed-Solomon codes give you incoherent matrices. And a Reed-Solomon code is a very explicit thing, right? It's like you take all polynomials of a certain degree, you evaluate them on the entire field. That tells you what you get. It's very explicit. But the problem is that the number of rows then in your RIP matrix will be like k squared. I don't want k squared rows. I only want roughly k rows. So that was like, when Bourgain and others picked up this problem in 2011, that was what they were trying, the barrier they were trying to break. They were like, nobody in the world knows how to beat k squared rows if you want an explicit matrix. We know how. If k is very close to root n, we can beat k squared by a little. Instead of k squared rows, we can get k to the 1.999 rows. Our method is complicated, and it uses a lot of analytic number theory to define what the matrix is and to prove that it works. Okay, so that's kind of the state of affairs right now in explicit constructions of RIP matrices. It's like even with using very hard math, no one knows how to do much better than k squared. So that's considered kind of I would say one of the major open problems in this area is, doing something non-trivial in this space with getting an explicit RIP matrix. So let me just show you that incoherent matrices give you RIP. So lemma, there's something called the Gersh-Gorin circle theorem. Let A be a square matrix with eigenvalues, lambda 1 up to lambda n, which are in C, complex numbers. Right. So again, remember that any square matrix has a full set of eigenvalues. They just might be complex because, if it's real symmetric, they'll be real. But a general real matrix A might have complex eigenvalues. Eigenvalues, if you just remember, are the roots of a certain polynomial. You look at the determinant of A minus lambda identity. That's a degree n polynomial. Its roots are the eigenvalues. And by the fundamental theorem of algebra, it has a full set of roots, but they might be complex. So anyway, look at these eigenvalues. The Gersh-Gorin circle theorem says that all eigenvalues of A. So, okay, actually, let me phrase it. I want to make sure I phrase it the right way so that it's correct. For each eigenvalue lambda of A, there exists some I such that if you look at AII minus lambda, it's at most the sum of J not equal to I of AIJ. Okay. So what it says is every eigenvalue of A lies in a complex disk around some diagonal entry of A of radius equal to the L1 norm of like the rest of the row. Right? The rest of the row without the diagonal. Okay. Does that make sense? So I only have 20 minutes left. It's the proof of this is like super easy. Even if I give you no hints, if I told you to prove this, you could do it yourself very quickly. You just basically, so I'll just put it in the course notes. Okay. But maybe the summary is just like for every eigenvalue, there is a corresponding eigenvector. So there is an eigenvector x that corresponds to lambda. Just look at what happens when you multiply A times x. And look at the ith entry of A times x. The ith entry of A times x needs to be lambda times xi, right? Because it's an eigenvector. So that could, just, and then you write down what the ith entry of a times x is in terms of a. It's the dot product of the ith row of a with x. That needs to be lambda times xi. So that constrains what lambda could possibly be. Right. So that's basically the proof. Full details in the notes. So now the lemma is that if pi is alpha incoherent for alpha at most epsilon over k minus 1, then pi satisfies epsilon k RIP. Okay. Remember what it means to be alpha incoherent? It means that all the columns of pi have unit norm, and all the dot products of different columns, the dot product has magnitude at most alpha. So what I'm saying is that kind of all these, right, what I'm saying is that, yeah, that's exactly what I'm saying. All the columns have unit norm, and the pairwise dot products are at most alpha. And what we saw in PSET 1 problem 1 is if you use Reed-Solomon codes, for example, the number of rows you need to get an alpha incoherent matrix is roughly 1 over alpha squared. It's like 1 over alpha squared times some log n factors. Okay. So 1 over alpha squared here would be k squared over epsilon squared, which is why you end up with item 2 saying you need k squared rows, because alpha squared is 1 over alpha squared is k squared. And the proof of this is just using the Gershgorin circle theorem. So the proof, we want to look at the eigenvalues of basically pi s transpose pi s for s having size at most k, right? So pi s is like, just keep the columns that are in S, where S is a subset of columns. And what we want to say is that we want these to be all in the interval 1 minus epsilon, 1 plus epsilon. That's what it means to be RIP. But the Gershgorin circle theorem says that all the eigenvalues lie in a complex disk of radius. Well, in fact, there's a real symmetric matrix, so all the eigenvalues are real. So it says that all the eigenvalues are close to the diagonal. How close are they to the diagonal? The sum of the rest of the row. What is pi s transpose pi s? It's a k by k matrix where, in the there are these k different columns, and it's the Gram matrix. You're looking at the dot product of these different columns. So in the diagonal, you're taking the dot product of a column with itself. And since it's an incoherent matrix, all the columns have unit norm. So the dot product of a column with itself is 1. And all of the off diagonals are at most epsilon. So Gershgorin circle theorem says let's call this matrix A. All the eigenvalues are some diagonal, all the diagonals are 1, plus or minus the sum of the off diagonals. But this is like at most, and I should say this is not epsilon, this is alpha, because it's alpha incoherent. But there are k minus 1 off diagonal entries. Each one is at most alpha. So this is alpha times k minus 1, which by choice of alpha is at most epsilon. So it's really kind of an immediate consequence of Gershgorin. Okay? So that's how you get RIP matrices. And now in the remaining 15 minutes, what I'll do is I'll try to prove that RIP implies that basis pursuit works. So I'm going to prove this claim. So any questions before I prove the claim? No? Okay. So let's get to work. Okay, so the theorem is that if pi satisfies epsilon sub k 2k RIP, for epsilon less than, I think we need to like square root of 2 minus 1, which, let me plug that into a calculator. That's around 0.414 or something. Then x tilde equals basis pursuit applied to pi x satisfies what I said. Okay. So let's prove that. And this particular choice of parameters is due to Immanuel Candice in 2008. But the fact that RIP gave you the fact that RIP equals basis pursuit let you get this kind of guarantee, it was already known before Candice. Candice just kind of gave the simplest proof that also got the best constant factors. So, I think the first proofs, instead of 2K RIP, they needed to make use of like 4K RIP or something. And instead of root 2 minus 1, they had like an even smaller constant that was needed. But, he kind of cleaned everything up and gave a slicker analysis. So first proof, let me make some definitions. T0 is a subset of N is the set of K largest entries. Okay, so I should say the set of K indices containing the largest entries of X in magnitude. Okay. And what do I know? I know that, remember, basis pursuit says min Z such that pi Z is equal to pi X. It will return Z equals some X plus H, right? Just H is just defined to be Z minus X. Okay. So let's just say that what it returns, I'm just going to call that thing X plus H, where H is just defined to be Z minus X. And then now what I'm going to do is going to say T1 is the K largest indices of H projected to T0 bar, right? So look at H, ignore the entries of H that are already in T0, okay? And now just look at the K next largest entries when you ignore the ones that are in T0. T0 might not be the largest entries of H, right? So T0 is the largest entries of X, but there might be some overlap with H. So that's why I'm only looking at H projected on the things that I'm not already, I'm ignoring the things that I've already counted. And then T2 is equal to the next K largest indices of, H sub T0 union T1 bar. T3 is the next K, etc. Does that make sense? So it's very similar to what we did when we analyzed the Kramer-Ward theorem. Okay. And notice that this thing here, that's just the norm of H, right? Just by definition of H. So really what I want to do is I want to say that the norm of H is bounded. Okay. So we want to analyze the norm of H, so let's do it. So we want to bound the norm of H. So what I'll do first is I'll just do triangle inequality. I'll say that the norm of H is at most the norm of H projected onto T0 union T1 plus the norm of H projected onto T0 union T1 complement. Okay. And then what I'll show is that we'll show that if you look at projection onto T0 T1 complement, first of all, this thing, H projected onto the complement, is at most H projected onto the not complement, plus O of 1 over root k times x tail k. And then we'll also show that h projected onto the not complement is at most O of 1 over root k times that same thing. Well, okay, so I'm drawing too low on this, but same thing. Okay. So good. Questions about this? Okay, so first let me state a lemma. I'm not 100% confident that I'll have time to prove the lemma. It's not that complicated of a lemma, but I'll write it down, and then I'll show you that once you have that lemma, you can prove Candace's theorem. So the lemma, let me state it here, and then we'll use it. The lemma says that if you look at the sum over j greater than or equal to 2 of the norm of htj, okay, this is at most 2 over root k times the L1 norm of x tail k, okay, plus ht0 union t1. Okay. So let's see, how can we use the lemma? So let's just now use the lemma to prove that what we want works out. So remember now what we want to bound, or we want to bound these two things that I told you. We want to bound this, and we want to bound this. So let's first start with the top one, because the top one is bounded in terms of the bottom one anyway. And then we'll deal with the bottom one. So if you look at ht0 union t1 complement, and you look at its L2 norm, that's equal to the norm of the sum over j bigger than or equal to 2 of h of tj. And then you just use triangle inequality. This is at most the sum of j at least 2 of htj. Okay. And then you just use the lemma on the previous slide, which I didn't prove yet. This is at most 2 over root k times x tail k plus ht0 union t1. Okay, so that's easy. Okay, so now the thing that really we have to do is we have to bound the second thing, which is h projected onto t0 union t1, basically this thing. So that's the thing we have to understand now. Okay. Now, let's look at pi applied to h. So okay, now we want to, let me just write down what we want to understand now. We want to understand h of t0 union t1. Okay, so if we apply pi to this matrix, to this vector, pi applied to h t0 union t1 is the same thing as pi of h minus the sum over j the sum over j of at least 2 of hj. Okay, what's pi times h? Anyone? Let me distribute this pi. What is pi times h? It's 0, right? Remember, this is a solution to basis pursuit. Basis pursuit says pi z equals pi x. So z is x plus h. So it's pi x plus pi h equals pi x. So in other words, pi h is 0. So h is in the kernel of pi. Really? So what this theorem is really saying is that if you look at, RAP matrices have the property that, okay, yes, they have some non-trivial kernel. They have to, because they have fewer rows than columns. Okay. So yes, pi has some non-trivial kernel, but anything that's in the kernel is so-called smooth. If you look at its L2 norm, I can bound it in terms of its L1 norm divided by root k. It doesn't have any, basically what that means is it's like, what does it mean to be, what's the opposite? The opposite would be, imagine, it basically means that the mass is kind of well spread, I guess, is also what you can say. The opposite would be like if all the, do I want to say that? Actually, let me not try and, yeah. Okay, let me not try to interpret that the way I was going to say, but ultimately it's some statement about the kernel of an RIP matrix. If a vector is in the kernel, it satisfies a certain property. Okay, so anywho, pi h is 0. So this is equal to negative the sum over all j of pi hj. So now if we start talking about pi h t0 union t1, if we look at this thing, L2 norm squared, first of all, remember we're trying to understand. We're trying to understand the L2 norm of this vector. Now, t0 is k coordinates, t1 is k coordinates, t0 union t1 is at most 2k coordinates. Pi satisfies 2k RIP. So this is certainly at least 1 minus epsilon, 1 minus epsilon k times the L2 norm squared. And now I want to say that it's at most something. So, of course, the L2 norm squared of a vector is just the dot product of it with itself. So this is the dot product of pi h t0 union t1 with itself. But what is itself? It's also equal to this. So I can say dotted with minus the sum over j bigger than or equal to 2 of pi hj. So this is equal to the sum minus the sum over j bigger than or equal to 2 of pi ht0 union t1 dotted with pi hj. Okay. And in fact, this is exactly equality, but I can put absolute values anywhere if I want to. Okay. And again, I can write that h of t0 union t1 is of course the same thing as h of t0 plus h of t1, which implies that pi times that thing is equal to pi ht0 plus pi ht1. So I can do that decomposition and do a triangle inequality. This is at most the sum over j bigger than or equal to 2 of the dot product of pi ht0 dotted with pi hj plus the dot product of pi ht1 dotted with pi hj. Someone tell me, what is the dot product of ht0 dotted with htj? What is that dot product? And also, if you take the dot product of ht1 dotted with htj, what is that dot product? What are these dot products? They're 0, right? Because T0 and T0 and T1 and T2, all these TJs are disjoint from each other. So HT0 has a completely disjoint support from HTJ. And similarly, HT1 has a completely disjoint support from HTJ. So these are both 0. And remember, we talked about this with Kramer-Ward. We talked about this with JL. Like, if you have a JL matrix or a matrix that preserves L2 norms, it also preserves dot products. Okay? So the original dot product is 0. So the new dot product is also 0, plus or minus some error term. And that error term is going to be at most epsilon k times epsilon sub k. So it's like what epsilon you're RIP for times the norm of ht0 times the norm of hj. And then here you have plus epsilon k, the norm of ht1 times the norm of hj. Okay. So this altogether is at most the sum j at least 2 of epsilon, the norm of hj, times the norm of ht0 plus the norm of ht1. Yeah, these are all L2 norms. And this, I mean, again, these are vectors of disjoint support. So if you squared them, if you squared each of these norms and added them together, you would get the norm squared of the union. And let me write it like this. So this is at most like this is at most twice the max of the two norms. Which is at most twice the norm of the union T0 union T1. Now let's just do it like that. But I mean, you can show that, in fact, maybe I'm running out of time here. So you can show that this thing is at most square root 2 times the norm of ht0 union T1. This is square root 2. So in summary, if you compare, let me just try and close this out since we don't have that much time left. If you compare this with this, kind of what you have is that 1 minus epsilon k, the norm of ht0 union T1 L2 norm squared, is at most the sum j greater than or equal to 2 of epsilon k times the norm of h times the square root 2 here, the norm of ht0 union T1 times the norm of h tj. Okay. So you can factor all this out. This is equal to the sum, maybe root 2 epsilon k, the norm of ht0 union T1 times 2 of the norm of htj. And this is exactly that lemma again, right? That lemma says if you have the sum of the norm of htj, it's bounded. So you just apply the lemma. This is at most root 2 epsilon k, the norm of ht0 union T1, L2 norm times O of 1 over root k times the L1 norm of the tail plus the other thing, which is ht0 union T1 L2 norm. Okay. So now everything looks great. You've basically bounded something in terms of itself, and now you just rearrange. And let me not do that on the board because it's just basically some algebra moving things around, but you can check the notes. I'll put it in the notes. So that's that. Modulo me having not proven the lemma. I'll put, I don't know if I want to spend time on the lemma on Monday, maybe not. I will just say, I'll definitely put in the course notes. And maybe what I will say is the way to prove the lemma is using shelling. So if you don't shelling, you're going to see it in the notes, but it's the same exact idea we used when we proved the Kramer-Ward theorem. So you basically, remember we partitioned the coordinates in decreasing order of magnitude in blocks of k. We compared the norm of the kth block with the norm of the k minus first block. That was the shelling idea. And it's the same exact idea that's used to prove this lemma as well. Okay. And I should just say that, where does the root 2 minus 1 come from? Why is there a root 2 minus 1? Basically, the reason is when you do the algebra and move things around here, you're going to end up saying that, this thing is bounded by something, and you're going to have to divide by something. And the thing you divide by is not going to be positive unless epsilon is sufficiently small. And you need it to be positive since otherwise it would flip the sign of the inequality. So how small enough does epsilon need to be to make that denominator positive? It's root 2 minus 1, which again, you'll see in the lecture notes. So